Suppose you'd like to estimate the proportion of voters in your town that plan to vote for Party A in an upcoming election. To do so, you take a random sample of size n from the likely voters in the town. Since you have a limited amount of time and resources, your sample is relatively small. Specifically, let's suppose that your n is equal to 20. After doing some sampling, you find out that 6 people in your sample say that they voted for Party A. In the previous election, we know that 40% of voters voted for Party A. So let's take a look at this problem from both a frequentist and Bayesian perspective. And the key that we want to take away from this is the difference between the two approaches. So in a frequentist approach, we need to start with a point estimate. So our point estimate, p hat, is equal to the number of people who voted for Party A divided by the total number of people in the sample. So that's 6 divided by 20. So my p hat is indeed 0.3. So frequentist approach would tell us that what we saw in our sample is in fact the true mean. Okay. Now, if we take a look at the standard error here, our standard error is equal to the root of p hat times 1 minus p hat divided by n. Okay, so you can see that by virtue of making this assumption, not only do we change our probability, our belief in our probability, we also change the standard error. Okay, so our standard error ends up being approximately, based on a 0.3 p hat, 0.1025. All right, so a confidence interval for this, again, we can fuss about whether or not we think 20 is enough for a proper confidence interval, but it's p hat plus or minus 1 point, let's call it 1.96 times the standard error, which gives us a confidence interval in around 0.1 to 0.5, somewhere between 10 and 50. Okay, so we can talk about this being approximately equal to 0.3 plus or minus 0.2. Okay, so that's the sort of the frequentist approach. Our point estimate is 0.3. Our 95% confidence interval leaves us somewhere between 10 and 50%. Is this data consistent with what we saw? Sure, 0.4 is in that confidence interval. Okay. So there's nothing wrong with this approach. And there won't be anything wrong with the Bayesian approach either. Okay, but the Bayesian approach would approach the problem from the following perspective. So the Bayesian folk, they say that we know something about the true probability already, right? So the probability given the data has some sort of beta distribution. So in this case, we know that 40% of the people voted for party A. So it might be beta of 4 and 6. 4 voted in favor. Okay. And then 6 because 6 plus 4 equals 10. And again, very roughly, 4 out of 10 is 40%. Right, so 40% of the previous voters voted for party A. Okay, so we might make some claim like this. Now, given what we just saw, we need to update what we know. So now we have a beta distribution is 4 plus the 6 that we just saw vote here. And again, if we had 10 total, right, the 6 plus 4 gave us 10. So now we've got our 10 plus the new 20 that we polled. Okay, so this is going to give us a mean of 10 over 30, which is 0.3 repeating. Our posterior standard deviation is the root of 10 times 20 over 30 squared times 31. And so that's 0.0847, give or take. And so our confidence interval here is going to be something like 0.33 repeating plus or minus 1.96 times 0.0847. And so our confidence interval is more like 0.167 up to 0.499. Okay. So again, with this information that we had previously, it pulls the mean more toward 0.4 than it was toward 0.3. Our confidence interval looks something like 17% to 50%. So both approaches here conclude that there's a substantial uncertainty about the probability with a sample that's this small. The frequentists say that the point estimate is 0.3, and that should be the true mean, whereas the Bayesian folks say that it's the true mean is probably closer to 40%. And again, by and large, both approaches say the same thing, but you can see here that the selection of our random sample gave us the 0.3, which gave us the standard error because it gave us the p and the p hat and the 1 minus p hat. Here, our choice of prior, that sort of helped us interpret this that helped us get this mean and the posterior as well. So again, in both cases, we've got the approach we're taking, it sort of leads us to a different conclusion. And that's, again, neither is particularly wrong in this case. They just are different. And when you set up a machine learning algorithm, or you try to interpret a problem, be sure you know whether you're doing it from a frequentist or a Bayesian perspective.